And let's start with a simple circle. Well, I don't know if it is simple. We're going to find out now. Here is a circle, and I'll give you one, or in fact, maybe you can tell me what are some facts about a circle, and you can raise your hand if you're willing to share over audio, or you can put it in the chat. What are some facts that maybe could come in handy as you begin to solve this question? I don't want the answer, but I just want some basic just ideas that maybe can help us. And Bouclair, I see that you have your hand up. Tell me one fact that comes to mind when you look at this page.
We know circles have a radius, sir.
They do have a radius. And what do you know about? So I'm going to say that's a radius. What do you know about the radius of a circle?
It's the same everywhere. Everywhere you put it, it's the same.
Yes, exactly. And so another way of us showing on a drawing, it looks a bit like whiskers on a cat or whatever, is we just put two lines that are the same. So thank you, Bouclair. Okay, now that is quite a helpful thing. Now what you guys need to do is find the size of the angle A that is just chilling over here. And then one of the options here is going to be correspond to that. So I want you to go ahead and see if you can, and then when you're ready, I want you to lock in your answer, A, B, C, or D. Hi, Tando. And also, while we are answering this question, who is new? Whose first lesson is it today? Corinna, is it your first lesson today? I feel like I might have missed your name earlier in the week, but is it? If it is, welcome. It's good for you. It's lovely for you to join us. Anybody else who is a new student? Or Corinna, have I just missed your name before and not seen it? Let me know in the chat if you're new. Just say new in the chat, and we can give you a nice Maths Live welcome. Oh, okay. No, that makes sense, Naledi. Thank you. I was like, I hadn't seen that name before. No problem. Tando is new. Welcome, Tando. It is very cool that you can join us today. I didn't introduce myself, so let me rather do that. My name's Peter, or Mr. S, or Teacher Peter, if you like. Those are all options. And I would normally do a more formal introduction, but today was just a bit of a quick getting going, but it's lovely to have you here. Okay, so what I'm going to say is I know that all triangles add up to 180. So I'm going to go 180 minus 98. And what do I get for that? I think I'm going to get 82, right? That is what is left. But that 82 needs to be split between this angle over here and this angle over here. But because this is an isosceles triangle, because it has two equal radii, we can say that angle A equals 82 divided by 2, which is going to give me 41. Now, the answer that then seems to come to mind is option C. The thing is, when you are doing a geometric calculation like this, you not only have to find the value of the angles, but you also have to support what you are saying with a reason. Now, I'm not going to concentrate too much on the reasons today. Today is going to be about just getting a feel for numbers. But whenever you make a statement like 180 minus 98 equals 82, you normally need, well, you need to support it with evidence for why you're making that statement. And so the reason that this one, we'll go over reasons in future lessons, but it's, the sum of a triangle adds up to 180. And here, that you have the opposite sides are equal, giving you an isosceles triangle. Okay, so each of these things going forward is going to have a reason, but for today, that's our first lesson. We're rather just going to focus on the basics. Okay, so what are the basics about circles? Well, they have radii, and radii are equal, which mean you get isosceles triangles popping up all over the place. And that is something that we need to remember. So give me a thumbs up if you followed that one. Give me a thumbs down if you didn't follow your first circle geometry question. Okay, fantastic. Now, turns out there are all sorts of things in circles. I will just give you a little, let's see if this is working here. Give you an example of how this works. Come on. Let's see if this will work now. My internet, it says my internet's not happy. Let's have a look. Okay, so this is a lovely little program called GeoGebra. And what GeoGebra allows us to do is to see what happens if I stretch this out. Now, that's rather interesting. You notice that the angles are changing, but they're still staying the same. And the reason that is happening is that these two sides are radii. So because these two are equal, that and that one, these two base angles will always be equal. And so the name or the reason we use to describe that fact is base angles equal or all radii. Okay, and whenever we have, I'll even draw another circle. Whenever we have a circle, excuse my circle, it's a bit dodgy. Whenever we have a circle, if we have two radii and they're joined by a line from one point on the circumference to the other, that will create an isosceles triangle. Now, for bonus points, what is the line which is red going to be called? For bonus points, what is the line that is red going to be called? This red line that is sitting up here. It's got a fancy name. And the fancy name, it sounds a bit like a musical thing. It's called a chord. So when you've got one line, when you've got a line that goes from one point on the circumference to the other, that is called a chord. And that word will come up again in future lessons, but I just thought I would point that out to start with. So chord is one thing over there, and then these things over here are radii. So the green ones are all radiuses, or plural form would be radii. Okay. Now, let's go and do some more practice questions. So, let's have a look here. This is just going to be using triangles. So this is just a bit of triangles. I want you to find me the value of x in this triangle, and I want you to find me the value of y and x in this triangle. See if you can do that. Trying to get something out of my while you do that. Technical glitches today. Okay, so pop your answer in the chat when you feel like you have one. And then okay, so okay, so in the first one, we should get that x is equal to 68 degrees. Now, if we think about why that is because this side over here and this side over here are equal, which means the angles that are opposite the side will also be equal. So x is equal to 68 degrees, okay? Now, what we're going to get is, if we're going to give a reason, we're just going to say angles opposite equal sides. Angles opposite equal sides, because that's literally the reason for this. X is 68. But we'll go over reasons in more detail in future lessons, but I'm just going to start putting them in now. Then for B, I'm going to say, I think this X and this 34 are both opposite equal sides. So I'm going to say X is equal to 34 degrees. And then I'm going to say angles opposite equal sides. So that is equal to 34. And then to figure out what Y is, well, now I'm going to say Y is equal to 108. Oh, goodness gracious, my pen is misbehaving. 180 minus either 34 minus 30. Actually, let's do that one. Minus 34 minus 34. And that is because of the sum of angles in a triangle. So we go sum of angles in triangle. Excuse my writing. I'm squeezing it into a small space today. So what is Y going to be? It is going to be 120 for the 30s. Take away another 8. It's going to be 112. Did anybody else get 112? Let's have a look at the chat. Give me a thumbs up if you followed my logic there, unless I made a silly mistake. So we know that if we have sides that are equal, then we know the angles that are opposite those sides are going to be equal. And then in this case, we got the two angles, but then the third angle, we just get Y over here. Give me a thumbs down if you didn't follow that. I just want to get a sense of where we're all at. Give me a thumbs up if you followed. Give me a thumbs down if you... Okay. Fantastic. Okay, well then let's... Should we do one like that? No, let's not worry about that one. Okay, let us do... let's do D and E. D and E. Can you find the value of X and Y in... so you want to find that one, and you want to find that one. And then over here, do you want to find that one? In fact, you just want to find X, but you're going to have to use all of them. Now, this is still actually triangle geometry, but we're just doing a bit of revision. Oh, I can see, okay. So I can see lots of students have said, well, they need a bit more help. So let me slow down and let me assist you with D. So what I want to point out for D is that this side and this side are equal, which means that if that's angle X over there, whatever angle X is, this is going to be the same. So this will also be angle X. So those two must be the same. So I'm going to even start by saying, look, angle DFE is equal to X. And the reason it's X is it's angles opposite equal sides. And those equal sides are the things in yellow. Now, I want to find a value for X, but I want to use the fact that I have 3 angles in a triangle. Who can tell me what I'm going to do next? Let me do that like that. Okay, Sanako, let's go to you.
So can't we say the sum of a triangle minus the 40 degrees, and the answer that we get, we divide it by 2 to get both the x's.
Yeah, exactly. So I mean, there's different ways we can do it, but I like what you said. I'm just going to say, look, x plus 40, okay, is equal to 180. Because we know all the angles in the triangle. Now, once you get really good at this, you can do even shorter methods than that. But would you agree with that?
Yes, I would.
Okay, now what do you think x is in this particular question?
So my answer here is 70.
Yeah, and I agree with you. So let me quickly just finish drawing the sum of angles in triangle. So the reason it has to be 70 is you can say here 2x is equal to, if you take away 40 from both sides, you get 140. And then if you divide both sides, there's a 2x equals 140, then x must be equal to 70.
Yes.
And you are quite correct. Now, since you've got 70, could you help me get y? Because we've just figured out that this is 70 and that is 70. What do you think y is going to be?
So can't you say angles on a straight line?
Perfect. What do angles on a straight line add up to?
I think isn't it 180, sir?
Yes. So if the x is 70, what does the y have to be? Or we can say 180 and then minus the 70,
It gives us 110.
110, yes. Cool. Sorry, my writing is going a bit dodgy. And then the reason is going to be angles on a straight line.
On a straight line, yes, sir.
Yeah, angles on straight line. And basically, angles in a straight line will always add up to 180, the same way that angles in a triangle will add up to 180. And angles, we just use the abbreviation A with this little angle symbol with a apostrophe and an S. Okay, nicely done. Let's go to Sinako and then Boucle. Oh, Boucle's question. Okay, Boucle. Or have you maybe got the answer for E?
No, I wanted to ask, could we not use also exterior angles of a triangle?
Ooh, yes. You are quite correct. So there is a theorem called the exterior angle of the triangle, and it is equal to the sum of the interior opposites. So basically, the blue one will be equal to this one and this one. And so you could actually do it in one step like that. Perfect. Absolutely. All right. Let's try and do E using that same idea that we use now. See if you can do E for me. Okay, my graphics pad is working properly again, so now I can. Let's see. Do we know that that and that are equal? So I think. So this, and this, they're not actually all equal. So let's make that a, what do they add up to? So I want you to put the answer you get for X in the chat when you get it. For those who have joined us late, we're just doing some basic triangle geometry problems. We did some circle geometry to start with, but we're just sort of getting used to this world of geometry today. That's kind of it's like the intro lesson to what's called Euclidean geometry or circle geometry. But at the moment, we're doing triangles. So x plus 2x plus 20 equals 180. And the reason is isn't x equal to 35? No, I don't think so. So now, go on, let's oh, wait, maybe we're going to see now. It probably is, yeah. I haven't solved it yet. So, what do we need of our reasons? Sum of angles in triangle. And so we're going to get 4x plus 20 is 180. And then if we take away 20 from both sides, we get 4x equals 180 minus 20. So then what is x going to be? What do we think x? Pop your answer in the chat there. Because we knew these two were equal. So that and that one were equal. But then this one over here was 2x plus 20. And all of those together added up to 140. So 180. Okay, so we divide both sides by 4. And then we're going to get x is equal to 40 degrees. Nicely done, Tando and Nomfundo, Lady. Okay, so one of the important ideas that's going to come up quite a lot in circle geometry is actually triangles and isosceles triangles. And so the main way that isosceles triangles come up is in radii of circles. So whenever you see a circle, whenever you have two radii, and those two radii are joined by a chord, then that will be an isosceles triangle. And then the theorems that we've been talking about now so far today will come into play, and you need to be able to solve for the unknown angles and sides. Give me a score out of 10, how you're feeling about the stuff we've done so far, where 10 is perfect, 0 is no understanding, 5 is maybe like in the middle. Give me a score out of 10 about how you're feeling about the stuff we've done so far. And be honest, because remember, I can't always read body language. And so the way I know if my pace is good for the class is if based on the scores that I'm seeing and if they're going in the right direction. Okay. Awesome. Okay. Well, then let us go to just some, before we go to our brain break, some words that go with circles. So you need to be aware of different types of words that deal with circles. So the ones that we've dealt with so far, if I have something like this, it's called a radius. And I think all of you know, if you take, okay, I kind of missed the center there, but let's pretend I went through it. That is called a diameter. So most people know about that, although you may not. And then if I go around the outside, what is the word for the perimeter of a circle? Who knows what the word for the perimeter of a circle? Okay, so let's go to Boucle. Let's have a look if I can see your little icon. There we go. Boucle, let me know. What do you think is that little blue thing I drew there, that little blue fence?
Circumference.
Yes, circumference. So that is the fancy word for the perimeter of a circle. Often we use the letter C for circumference. Okay, those are the well-known ones, but there are some other ones that you need to know about. What about a line that just touches the circle in one place only? That is called a tangent. A tangent to a circle. You know, they talk about people going off on a tangent when they like aren't focusing on the main topic. It comes from maths where you get close to the circle, you're like talking about the same topic, and then you just go off and talk about something totally unrelated. If you've ever heard that saying, like going off on a tangent, this is where it comes from. Give me a smiley face if you've heard the saying, that person's just going off on a tangent. I want to know if you've heard that saying before in popular language. An unsmiley face if you've never heard it. Okay, maybe it's just an old person thing. Okay, so, oh, Nomfundo's heard it. There we go. Pila, no, not so much. Okay, well, you never know. So, straight line, yes. So, but this is, a tangent is a special straight line which only touches the circle in one place. Okay, now what are some other special words we need to know about? Oh, okay, we spoke about this one earlier. What if you go from one point on the circumference to another, but you don't go through the middle? That is called a chord. And it sounds a bit like a musical term, but this is the mathematical term, a chord. So we have that. And then there are some other ones, but I'm not going to go. Oh, sorry, there is one other one I really want to talk about. This is important. So if you have a quadrilateral that has all its vertices on the circumference of a circle, so basically it's a four-sided shape where all the vertices land on the circumference of the circle. What type of quadrilateral is that called? What type of four-sided shape? It's got a fancy word in circle geometry. Yes, this is called a cyclic quad or a cyclic quadrilateral, and they can come in different shapes and sizes. For example, your cyclic quad could also look like it's squeezed into one little corner like that. Okay, so that could also be a cyclic quad, as long as the four vertices are on the circumference of a circle. And so a cyclic quad is something which we are going to mention going into the future. And then I see, oh, a segment. Okay, yes. Okay, so that's actually true. Let me mention a segment as well. So when we talk about a chord, so let's say we have a chord that goes from one side to the other, the chord divides up the circle into two pieces. Let's say on this side, we'll call it the major segment. So major segment. And on this side over here, the smaller piece is going to be called the minor. I've actually run out of space. Let me go minor segment outside. I'll make it in green and then I'll color it in minor segment. So the minor segment is here. The major segment is this area over here. And the line in between them is a chord. Okay. So those are some new words that you're going to see me using them in future. But for today, I just want you to be aware of what are those words and what do they do. Cool, everyone. It is time for our brain break. So let us all stand up. We are going to do some exercise just to loosen ourselves up because we've been learning for half an hour. And apologies, the angle is different, but I'm using just my laptop today. So let's start with some deep breaths. Breathe in. Breathe out. One more deep breath. Okay. Then to loosen up, let's roll our shoulders. We're rolling backwards, and then we're going to roll them forwards. Yeah. Then we're going to shake out our arms. We want them to feel like they're nice and loose. Shake out this arm, nice and loose. Shake out this leg. Shake out that leg. Oh, that feels very good. Shake out the leg. All right. And then let's just do a neck stretch. So just have your neck to the side. And then on this side, and this, like this. And then let's do a tricep stretch like this. So hold that. And then switch to the other side. Okay. And then shake out those arms, shake out those legs. Okay, so we've got some oxygen in our body. Our bodies are a bit looser. They're less tense than they were. Now we need some blood flow. And to get blood pumping in our body, we are going to do something called a jumping jack. I'm going to take off my tracksuit because otherwise I'm going to thing. And then we are going to do 15 of these in 3, 2, 1. Let's go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 50. And that is that. Okay, tell me how you are feeling. Do you feel refreshed after the brain break? Do you feel like your brain has had a break? Before there's us jumping up and down, before we move on, we're just going to have a go at these Maths 24 cards. Can you tell me how to make 24 using either of those sets of 4 numbers? You need to use every number, and you can only use plus, minus, times, or divide. Oh, I feel alive. I feel alive. Who else? Come on, you know that break helps. Let me know in the chat if you feel a bit like your concentration has been brought back to you. Okay. Fantastic. Okay. We all know how to play Maths 24, except for anybody who's new. You have to take the 4 numbers and make 24. So Sanako has put an effort in. And the first one has already fallen 4 times 3 times 2. Why is my thing off here? Times 1. Okay, 4 times 3 times 2 times 1 gives us 24. And so that is the red card has fallen to Sanako. Can anyone do the blue one? Can you make 24 using 6, 7, 4, and 2? Any ideas? And Takiso has said 7 times 2 is 14 plus 6 plus 4. And Takiso, yours is, you are the winner. Well done. So well done to Takiso and Sanako. You've done very well. All right, everyone. It is time to go back to our circle geometry story. So here's another multiple choice question. Which of the following diagrams shows a chord? Is it A, B, C, or D? Which of the following diagrams show a chord? Well, you guys know what a chord is, so there we go. It is indeed B. C is a tangent. D is a radii, and then I suppose A is a line that just got lost. Okay. Cool. Choose the option here. What is another name for the perimeter of a circle? Is it A, B, C, or D? Indeed, ladies and gentlemen, you know your terminology. This is a circumference is the thing around the outside. I do see one word, though, that I didn't... Oh, flip, look at me. I'm making a mess here. I do see one word, though, that I didn't talk about, which is a sector. So what is a sector? A sector is if you have 2 radii. It's almost like a sector of an orange. That would be a sector in a circle, which is different to a segment. A segment is when you divide the circle up using a chord. And then like that would be the small segment, minor segment, and then this side would be the major segment. Okay, you're doing very nicely. Ooh, something interesting. Okay, now, before I take you on this fun little journey, I just want to point something out to you. If we talk about a circle, and this is another word we haven't spoken about yet a little bit, but if I have 2 points on the circumference, the one way of joining them is to join them with a chord. But there's also a curved way between the 2 points over here. And since it doesn't go the whole way around, it's not a circumference. what is this yellow line over here called? It's a curved line. And I just want to make sure that we know some more terminology. What is that yellow line called? It's not a chord. The red line is called a chord. The yellow line is called an arc. And the yellow one is called the minor arc. And if I had a line going the whole way around, the green one would be called the major arc because it's the bigger one. Okay, so lots of words today. Oh my goodness. Now, if we think about the chord or the arc, they both start at the same place. I'm going to call them C and D because I'm looking at the drawing here. There's another fancy word that we use in circle language, and that's if we subtend an angle. Let me actually show you what it means. We say that the chord CD subtends an angle at the center. So it's using the chord or it's using the arc as the base, and it's making an angle at the center, at the point A. The fancy word for building that angle is called subtending, or subtending an angle at the center. Subtending an angle at the center. So that's an idea that's quite important, and I just want you to be familiar with that. But you can also subtend an angle from the same chord at the circumference. And so we can also, the green one, we can say subtend an angle at the circumference. And I'm going to use abbreviations for angle and circumference. And so often this theorem, this fact that we're going to investigate is called the arrowhead theorem because of the sort of arrowhead-like shape. But the main idea is you have some arc or chord, and from that as a base, you make an angle at the center, and then you make another angle at the circumference. Now, let's go and look at a live animation of this idea. So that we kind of can make not just like a drawing, a static drawing, but we can actually play with it a little bit if GeoGebra is going to behave. Okay, let's look at this. So the red one is the angle at the center, and then this one is the angle at the circumference. Now, the good news is, what's quite fun is I can move these things around, which is kind of fun, isn't it? Look, I can make it look more like a triangle where the angle is 180 and that's 90, or I can make it like go to let's say 130. So the angle, so the arc CD is quite big here. So the angle at the center is quite big. And then look at the angle of circumference. And then if I make it, if I like, I can bring it right down to maybe like something smaller. Like, should I make it like 50 degrees? That's quite a narrow. So you're making an angle at the center, and then you look at the angle at the circumference. Now, it feels like there's a relationship between the angle at the center and the angle at the circumference. Let's actually even move this. Oh my goodness, I can even move this right over. So the shape looks different. Now it looks a little bit, yeah, almost like a bow tie almost, hey? Like, yeah. So we've got like the arrowhead, and then we could move it even to there as well. Can anybody spot anything about the relationship between the angle at the center and the angle at the circumference? Who has some ideas? Who would like to share anything they observe? Maybe they've noticed something that seems to, even though we move it around, it seems to stay the same. So we'll notice here, that's 80 and that's 40. Let's change this to 100. When that's 100, that's 50. Yep. And so Kiso has said that the angle at the center is double the angle at the circumference. Sorry, the angle at the center is double the angle at the circumference. Yeah. Or we could say the angle at the circumference is half the angle at the center. And this is an important fact that you need to get used to for circle geometry. The quick way of saying it is, or the shorthand reason for the theorem is angle at center equals twice angle at circumference. We'll worry about reasons more in future lessons, but when you use this fact, you say angle at center equals twice angle at circumference. Okay? And that is using the idea that the angle at the center is twice the angle at circumference. Now, I'm not doing proofs. There are proofs that we can do at a later stage, but for now, I'm just getting you familiar with the main ideas. So let's go and see this question in action. What is the size of angle H using the fact or the theorem that I just showed you? What is the angle of H going to be using the theorem that I just showed you? So to me, it feels like that is the arc, or if I connected it, the chord that's important. It makes an angle at the circumference, or subtends an angle at the circumference, but it also makes one at the center. And the one at the center is going to be double the angle at the circumference. And so the correct answer will be C. Okay, awesome. I like what I'm seeing. I like it very much. Okay, let's go to this question. Can you find me the value of angle X? Using this new fact about circles that you've just learned about for the first time. What do you think the size of angle X is going to be? I think X is going to be 124, but not exactly the same. It's going to be half that, which is 62. And if I'm being very official, I would write angle, official, if I want to get full marks when I eventually do this, angle at center equals twice angle at circumference. You'll notice I'm using an abbreviation for angle. 2 angle is also like that. And I'm also using an abbreviation for circumference with a dot. Okay, you guys seem to be getting this nicely. Little bit harder one. Which of the following is the correct way to write the unlabeled angle in terms of y? So here is y, and then the unlabeled angle is down here. And we want to say which of the 4 options do we think will be where the green highlighter is? Okay. So the first thing is, the big one is what? You can kind of see it, but the big one is the angle at the center. So the relationship between the yellow and the green one is the yellow one is twice the size of the green one. And so I think I should take y and divide it by 2. So y divided by 2, and that would be C over there. Awesome. And Tando agrees, Sanako agrees. Okay, awesome. Well, you guys are just doing so well. Let's just keep swimming. Can you find me the value of X for this one, this circle geometry question? Can you find me the value of X for this circle geometry question? Be careful here. Remember, this is the arc, or if I had to draw in the chord, I could also draw in the card. This is the base for which the angles are built. The angle at the center is going to be this one. The angle at the circumference is going to be that one. So now the question is, if we need to find what X is, we need to describe this relationship. So what do we think that's going to be? I think we have to build an equation. And we have to say the angle at the center. So we need to say the angle at the center is bigger than the angle at the circumference. No, it is already bigger. Sorry. Oh, this is sneaky. This is the smaller one. So if x plus 22 is the bigger one, what I need to do, and this is sneaky, is I need to multiply this by 2 to make them equal. Whoa, that is sneaky. Give me a thumbs up if you follow that. So if you know that this one over here is the big one. Okay, that's the big one, the little one over here. If I want to make them equal, okay, then you have to double the little one. Okay, whoa, that was sneaky. Now, can you find, so I'll put the reason here, angle at center equals twice angle at circumference. And I want you to find me what x is. This is such a sneaky question. But it's good to do some sneaky ones. You can't just do them. So if I bring this x to the other side, I'm going to get 2x minus x, and I'm going to get x is 22. Wow, that is crazy. But let me show you why this works. If that is 22, and then this is 22, what's 22 plus 22? It's going to be 44. And that makes sense because the angle at the center is double the size of the angle at the circumference. So the value of angle x is actually going to just be 22. But the angle at the center will be 44. The angle at the circumference will be just 22. Okay, everyone. So for today, the goal was just, I know, sneaky, but that was like end of the lesson stuff, you know, just to keep it interesting and exciting and show you have to stay on your toes. Okay, yeah, did I give you a bit of a fright there? It's because the little one is the smaller one, so you need to double the little one to make it the size of the big one. That was the sneakiness. So just to tell you where we're going in the next lesson, the first 2 lessons are all about circles and their center and theorems that relate to the circle and their center. So today, we mainly looked at when you have radii, you get these things called isosceles triangles, and those can be used. We also looked at the theorem which says, look, if you've got an angle at the center, it will be twice the size of the angle at the circumference. And then we also looked at general words and terminology around circles. In the next lesson, we're going to look at even more detail around facts about the center of a circle and so on. But it's been a good lesson. I've enjoyed teaching you. I hope you've enjoyed.